Water is the most essential ingredient of Earth's life support system. It flows through every human endeavour.
The International Atomic Energy Agency is an organization dedicated to ensure that nuclear technologies are made available for human welfare. In addition to our well-known work to make sure that nuclear energy is not diverted for military purposes, we also have a major program to ensure that nuclear technologies are used to meet basic human needs: health, water, agriculture, and on all these areas, we have a technical cooperation program that is operating in over 100 member states.
In ancient times, when tribes set out to find new lands, the basic need for fresh water guided them. Many faiths regard water as a link to the spirit of life. Our search for water still plays a major role in the exploration of Earth. Science is now going much further. The quest for water and potential life on other planets leads us to the stars. When a child is born every second, the demand for fresh water increases by the minute. We face an unprecedented need to understand water, to work wisely with this resource for now and for the future.
There is a dwindling amount of surface water. 1 billion people have no access to safe drinking water.
The United Nations Millennium Development Goals state access to clean drinking water is a basic human right. In pursuit of this goal, the IAEA's Water Resources Programme applies the science of isotope hydrology. But how can modern-day alchemists divine the elemental power of water? Isotope techniques are one of the most rapid and effective tools we have to define water.
But what is water? Water is made of water molecules. Every water molecule combines hydrogen and oxygen, but some are lighter and some heavier. Why is this? Hydrogen and oxygen have lighter and heavier atoms called isotopes. In oxygen, the lighter isotope, coloured yellow, is named oxygen 16, while the heavier one, coloured red, is oxygen 18. Differences between isotopes are so tiny, we need sophisticated measuring tools to trace them. This is where the IAEA laboratories step in. But why is it so important to know the weights of different water molecules? Isotopes are reliable indicators that can be used by scientists to identify different sources of water, its age, and how fast it moves within the water cycle.
Access to reliable water resources determines the health of all nations. Water is the driving force behind global and local economies. Water crosses all borders. The way a country deals with pollution or urban runoff has far-reaching consequences for the health of another. Agriculture is 100% dependent on reliable supplies of water, and the wheels of industry would grind to a halt without it.
The IAEA Isotope Water Mapping Project has learnt that aquifer systems are often linked to daily rainwater. Natural water cycles reveal how the well-being of one nation affects another. But how do water cycles work? In boiling water, which type of water evaporates first? Well, molecules with lighter isotopes leave the pot first. When seawater evaporates, lighter water molecules rise before heavier ones. And when it rains, which molecules fall first? Heavier ones. The further clouds travel inland, losing water on the way, the greater the proportion of light molecules in the water. Water falls to Earth. On its way back to the sea, it fills rivers, lakes, and underground aquifers. By measuring isotopes in these waters, scientists can trace the history of water as it moves through the water cycle.
Climate change and global warming has a negative impact on the availability of surface water. Rarely has any part of the world not experienced either a drought or a flood. Through isotope hydrology, we are trying to understand the processes of interaction between water and climate change.
From space, it's hard to believe we're approaching a world water crisis. But while water covers about 70% of the Earth's surface, almost 97% of this is salt water. That leaves 3% fresh water, mostly locked away in glaciers, icebergs, and snow. What's left are lakes, rivers, and deep aquifers. The sum total of available fresh water sources is just 1%. 1% of the planet's water for all life on Earth. Water is humble yet powerful. A single drop contains the key to life, and a flood can change history. Water shapes many national borders, and conflict over resources causes wars. The lack of water can turn a rich nation into a thirsty one. Recent upheavals in global weather patterns are teaching us valuable lessons. How we treat natural watersheds is linked to environmental stability and the future of our own civilization. The United Nations IAEA is taking initiative to share knowledge about water resources and build local and international capability so water becomes a common responsibility.
Water from separate places is often very different. Some might be fresh and young and some ancient. Knowing the age of water allows us to discover whether recent rains replenished it or if it is ancient fossil water. But how can we determine the age of water? There are many types of isotopes contained in water. The IAEA works with naturally radioactive ones. As time passes, these change. From the moment that rain becomes groundwater, radioactive water isotopes start breaking down into other atoms. As time goes by, the concentration of radioactive isotopes becomes less, especially compared to recent rainwater. We learn the age of water by measuring the radioactive levels of water isotopes.
Through isotope hydrology, we can now understand the history, the aging, the degree of recharge of underground water, and make sure that countries are using water in a sustainable manner. And we provide advice as what is the optimum use of underground water. We put a lot of focus on groundwater. Groundwater provides 2/3 of drinking water for the continent of Africa. We would like them to have as much available water, clean water, for their own well-being and survival.
When one pumps up fossil water, there's a risk of running out. This can disrupt a local ecosystem and lead to global environmental changes. Once an ancient water resource is defined by isotope testing, this information can boost a local government's understanding of its water supply. More detailed studies map out renewable freshwater aquifers or other potential water resources and help a country plan practical ways to use available waters.
I believe what we do in cooperation with many other organizations is vital in the next few years to ensure humanity has enough clean drinking water and that humanity is coping with the negative impact of climate change and global warming by making sure that our use of water, both surface water and underground water, are done in a sustainable manner.
In our continuing search for new water resources, water itself is our most faithful guide. As the basic need for fresh water grows stronger by the day, we must use all knowledge available to ensure that water remains as fresh, sweet, and abundant as ever.